So this video, we're going to look at a picture of a galvanic cell. And the key to a galvanic cell is it's got to be spontaneous. Spontaneous electron flow. Once we initiate the reaction, it does its thing and just keeps going. So this is like the process inside the battery of your cell phone when it's not plugged into the wall charger. It's going through a galvanic process in the battery that supplies the electricity to power the phone. So when we draw the picture of what a galvanic cell looks like, we have to draw it so that it's spontaneous, and we have to draw it so that we have half cells. And in those half cells, reduction occurs in one of them, and oxidation occurs in the other. You're going to hear me use the terms red and ox a lot for reduction and oxidation. A redox process, red and ox. So red and ox. So when we put these materials in two separate half cells, so think of it as two different beakers, we set up one half cell the way it needs to be set up. We'll talk more about that here in a second. And the other one, the way it needs to be set up, we connect them with wires. And when we do that, we can allow electricity to flow between the two half cells. So let's look at a picture diagram of what this might look like. I'm going to draw two beakers kind of close together. And each one's going to have some solution in it. And in those beakers, the solution that's in each beaker is different. The one on the left-hand beaker, we're going to put in zinc nitrate, ZnNO3 by 2. And this is aqueous. In the beaker on the right, we're going to put in CuNO3 by 2 in aqueous solution. So we have aqueous zinc and aqueous copper because those are soluble compounds, right? They're strong electrolytes. So what we really have here is a solution of zinc and nitrate ions, a solution of copper and nitrate ions. Now into the beaker on the left, we're going to place an electrode. These are a lot of times referred to as paddle electrodes or sheet electrodes. It's literally just a sheet of zinc, a small little sheet of zinc that's attached to a wire. So it's solid zinc. Over here on the right-hand side, we're going to put another paddle electrode in that's solid copper and connect a wire to it. Now, if we just connect these two wires, juice will start to flow at least for a little bit. But we're going to connect these wires through a voltmeter. If you've had any kind of physics class, you probably used voltmeters before. Think of it just as something that measures voltage or potential of electricity. Now when we hook these up, we have to hook them up in a special way. Remember I said we have to show this so that it's a spontaneous process. And when it's spontaneous, a galvanic cell, the electrons have to flow from left to right in our picture. So as we're looking at it, the left-hand half cell is where electrons have to come from and go to the right-hand half cell. So a lot of times on these diagrams, you'll see an arrow showing you the directions where electrons are flowing, from left to right. So zinc is being pulled out of the zinc electrode and up through the voltmeter to the copper electrode. So we can also put electron direction over there. Now by convention, the voltmeter is always hooked up with the negative on the left and the positive on the right. If you've used a voltmeter, the left-hand lead would be the black one, and the right-hand lead would be the red one, if you're using a standard voltmeter. Okay. So electrons are flowing from negative to positive. Doesn't look like it right here, but they're being attracted through to the positive side. The positive side is over here. The electrons are being pulled left to right. All right, so in our diagram, when we hook this thing up and let juice flow, it'll flow for a millisecond, and then it'll stop. Because as electrons start to move from one cell to the other, they're going to build up on one side and be depleted on the other, and the flow of electricity will stop. So to complete the circuit, we have what's referred to as a salt bridge. And a salt bridge is a glass tube, or can be a glass tube, it could be plastic, but that salt bridge contains a paste of an electrolyte that doesn't interfere with most any electrochemical reactions. Potassium nitrate is a really good paste to put in there because all potassium salts are soluble, all nitrate salts are soluble, so it's not going to interfere with any of the half cell reactions. So in this salt bridge, again, it's an electrolyte paste. And the end of each of the parts of the tube where it dips into the solution, there's what's referred to as a frit built into the tubing. And it's basically like a piece of porous stone, like pumice stone. They kind of look like that if you ever look at one. But it allows ions to pass through without just letting all of the material inside the salt bridge just dump into the solution. So frit at each end allows ions to pass. And it maintains neutrality, or maintains electroneutrality. That's really just a fancy term for completes the circuit. So it kind of acts like a ground wire. So in this cell, once we hook everything up and we got our salt bridge in place, electrons are going to flow from left to right. Why is that? Well, it's because copper likes to be reduced, likes to be in its metallic form more than zinc does. Copper is a jewelry metal. It's not a great jewelry metal because it'll turn your finger green, but it is considered one of the jewelry metals. So it likes to be in its metallic form, not in its oxidized form. Zinc is willing to be oxidized more than copper is willing to be oxidized. So as a result, copper will steal zinc's electrons. So when current is flowing in this cell, electrons are pulled out of the zinc half reaction. Well, that means that zinc is being oxidized. So oxidation is occurring on the left-hand side. Electrons are being pulled out. So when zinc is oxidized, the zinc paddle electrode, the metallic zinc, is being oxidized into zinc 2+ and released into solution. So zinc is being oxidized. Those electrons that are produced during that oxidation process are pulled to the copper side, where reduction occurs. Reduction is always the right-hand side. Reduction on the right, R and R, reduction on the right. During reduction, these electrons are coming in from the other side. They get to the copper paddle electrode, and what happens is copper ions, as they bump into that electrode with the extra electrons, will reduce. Okay. Not balanced reactions, not showing the electrons or anything, but that's the process that's going on. So as this thing, as you just let this sit and let it run, the zinc electrode is going to get smaller. It's going to corrode because it's being oxidized. Zinc 2+ concentration here is going up. As the electrons move to the other side, they get to the copper, they get reduced, the copper ions get reduced. This paddle is going to grow. It's going to get larger and get more coating and more coating and more coating of copper ions on top of that. So we refer to this as the zinc half cell, the copper half cell, the oxidation side, the reduction side. There's also an extra set of names for these. The oxidation side, the left-hand electrode, is always the anode. The reduction half reaction, the right-hand part of this galvanic cell, is the cathode. The anode is the negative electrode. The cathode is the positive electrode. Those are all terminologies that you have to be comfortable with. If I ask you where's the oxidation occurring, where's the anode, where's the negative electrode? It's the left-hand side. Where's the positive electrode? Where's the cathode? Where's reduction occurring? Those are all the right-hand side. Okay? So this diagram, as we have it set up right here, is drawn as a spontaneous galvanic process. There's a couple of diagrams in the book, and they're not real careful about showing that it's galvanic. In fact, the picture on page 906, I believe it is, shows a cell reaction, but it's not a spontaneous one because electrons are flowing from right to left when they hook that one up. Okay? So if you're ever asked to draw the picture of a galvanic cell given two half reactions, the zinc and the copper reactions, you have to set it up in the diagram so that it's spontaneous with what's on the left going to the right in terms of its electrons. And you'll have to have a salt bridge. You can just label it, you have to draw all the other stuff about it, but you have to have a salt bridge, you have to have a wire connecting the electrodes. Okay? So we're going to talk some more about galvanic processes. We're not going to draw a lot of diagrams though because it takes a long time. There's a shortcut that we're going to use to kind of tell us what the diagram looks like without having to draw the whole diagram. So we're going to come back, we're going to do some of those, we're going to balance some half reactions. We're going to use the same process that you guys used last semester that you didn't really enjoy so much because they were an acid and base solution, which complicated the whole thing. We're getting rid of the acid and base part. We're just doing them in aqueous solutions, so there's not a bunch of oxygens to get rid of and OH groups and things like that. It's just metal ions. So we're going to look at balancing the half reactions, balancing the electrochemical process with half reactions, and then look at how to do this diagram shorthand style. Okay?